Hello dear students, welcome back to Chandu Biology Classes, and this is our session 2 on thermodynamics, right? So in the last class we have seen thermodynamics along with these states of matter, that is gaseous states, right now. So in the last session I have clearly discussed the states of matter, that is especially here gaseous state, right now. So now in this gaseous state there will be some basic laws, that is what we can call Boyle's law, Charles' law, and next Avogadro's law, Gay-Lussac's law. All this we have studied, and along with that we have derived an equation called ideal gas equation, which is PV equals to nRT, right now. So those gases which obeys this ideal gas equation can be considered as ideal gas, right now. So this is a combination of what? Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law, right? Hope everything is clear in the last session, and I hope you have watched it completely, and I also solved the previous year questions of IIT JAM BT from this particular chapter, okay? So today we will be discussing thermodynamics, okay? For this thermodynamics, the basic part is states of matter, okay? That is what gaseous states here, okay? So if you haven't watched this session, I request you to, and I will suggest you to watch this gaseous states also, okay? And I hope your preparation is going well, and I hope you are using our this PCM series very effectively for your preparation. So where we are covering all the maths, physics as well as chemistry topics that are highly required for your upcoming IIT JAM exam, right? Yes. So let me check anyone in the comment box, right? So here today we will be beginning our discussion on thermodynamics. Thermodynamics. So in this chapter, and if you observe the previous year questions, so you can expect one question from thermodynamics, okay? Because we will be discussing about chemical reactions where some heat energy will be associated with the chemical reactions now. So whether the reaction is absorbed heat or released some heat during a reaction, like whether it is absorbing heat or releasing heat, we are saying it as endothermic, exothermic process. We are much familiar with these terms in our chemistry or biochemistry part right now. So it is very important to know the thermodynamics beyond the chemical reactions right now. So let's begin the session with the basic terms first. What are the basic terms we will be using in this thermodynamics, and after that we will be seeing the PYQs of this thermodynamics, okay, right. So look at this, what do we mean by thermodynamics? It states that it is the study of flow of heat or any type of energy into or out of a system during a chemical reaction, during a physical or chemical transformation is called thermodynamics, okay. And this thermodynamics, whatever we are studying here, it is applicable for macroscopic bulk properties, or it's a bulk phenomena I can say, okay. So something called statistical thermodynamics will be there, where we will be using for microscopic level, okay. So this thermodynamics, whatever we are studying, this is applicable for bulk properties, it's a bulk matter, like for a macroscopic systems I can say, okay, right. So now in order to understand this thermodynamics, so we need to know some basic terminologies, like here I used the term here system. So what do we mean by system, okay, and there is one more term called surrounding, and together we are calling it as universe, okay. This basic terminology we need to learn first, and how can we classify them further, this we will be seeing. And where do we use this thermodynamics in our daily life? See here, the main objective of chemical thermodynamics is whether a particular reaction is feasible or not, whether it is spontaneous or non-spontaneous, can be explained using this. See, predict the thermodynamics, predict the feasibility, or I can say spontaneity of a particular reaction, okay. It means there are some chemical reactions which are happening at higher temperature but not possible at lower temperature, or in vice versa right now. So that is what we are saying it as spontaneity of a chemical reaction. So this spontaneity can be explained, clearly explained using Gibbs free energy change, delta G. That is a very important topic, spontaneity process. We will be discussing about this spontaneity also, delta G, and what are the other along with this, what are the other things we need to look for making a spontaneous chemical reaction, okay. Here itself I am giving you a hint or a trick to, or a point to be remembered. For a spontaneous process, delta G, this is a thermodynamic property here. So this quantity must be negative, delta G must be negative for a spontaneous reaction. Okay, you should remember this. If delta is 0, you can say that reaction is at equilibrium. Okay, you just remember these important key points. Okay, because from these key points also we can expect a question. That's why I am adding here itself. So for a spontaneous process, delta G must be negative. If delta G is equals to 0, then you can say the reaction is at equilibrium. And other condition possible is delta G to be positive right now. If delta G is positive, then you can say it's a non-spontaneous reaction. Okay, if delta G is greater than 0, it can be considered as non-spontaneous reaction. You can remember these 3 points. Then next, for a feasible reaction, now we are saying thermodynamics says about or predicts about the spontaneity or feasibility of a reaction. Now for a feasible reaction, we can able to calculate the various types of energy like enthalpy change or internal energy change during the reaction. Okay, so what are the energy changes accompanied during a chemical transformation can be also calculated using this thermodynamics. Okay, and we can relate to each other. Okay, if for example at particular temperature T1, what is the enthalpy change? Then at particular temperature T2, now what is the enthalpy change? Okay, heat exchanged or heat absorbed or released, this can be calculated. Okay, are related to each other. Then next, this is also clear. See, for a feasible reaction, determine the extent of reaction under a given set of experimental conditions. Okay, and we can alter the experimental conditions to make it more productive or more possible yield right now, and derive the general thermodynamics laws and relations. Like we will be deriving some thermodynamic laws and relating them. Okay, these are the things we are going to do here, right? So first, what are the basic terms here? See, we are doing a chemical reaction. Let us consider this is a container in which we are doing the chemical reaction. Okay, for example, in this we are doing some chemical reaction, means the one which we are using for doing the chemical reaction can be considered as system. Okay, the remaining portion around this system, except the system, whatever the other portion is there, that will be considered as surroundings. Okay, so the remaining extra part here I can say surroundings. Okay, now there is a layer, whether it can be a real or an imaginary part, that is separating surroundings and system. This is the part now separating surrounding and system, considered as boundary. What is that? Boundary. Okay, so we have 3 parts now. One is system, which is under our observation, in which the chemical transformation or a chemical reaction or physical change is taking place, and the remaining portion is called surroundings. Now the real or imaginary surface, the part which is separating system and surrounding, is called boundary. Okay, hope everything is clear here. Now one more term is there, universe. So what is mean by universe? So universe means simply you can say system plus surroundings, complete thing is considered as universe, that's it. Okay, these are the very basic terms, I hope you know this. Okay, next, this system can be of different types now. Okay, so this system can be an open system, is very important to understand, open system, and I am saying one more is closed system and one more is isolated system. So what do we mean by closed and open system? See, open system means, see, during a chemical reaction there will be some matter in this container. Okay, so there will be some heat exchange between system and surrounding is also possible now. Yes, and this matter can also exchange is possible now if it is open. So now what happens, both energy as well as matter can be exchanged between system and surrounding, so that can be considered as open system. Now if this is a closed one, okay, if this this container is having some matter which is closed, if it is closed, there will not be any exchange of matter from system to surrounding right now. Therefore we can consider it as closed system, and in this closed system heat can be exchanged. How this heat can be transformed? Yes, if there is something here lower temperature, therefore the heat from our system to surroundings may takes place, our surroundings to system may takes place. So that is that is seen in the case of closed system. Okay, right. And isolated system means there is no exchange of heat and there is no exchange of matter, both will not be exchanged. You can remember this very basic terms. Okay, right. And one more thing here you need to know is, what is the best example of this open system? Yes, human body is in like we ourselves or any animals you can take. All this comes under open system. Okay, so human body or animals you can take, everything comes under this open system. Okay, and when it comes to closed system, you just take any closed container like a water bottle, okay, something like this comes under closed system. So for isolated system there is no exact example, but we can consider the thermo flask which we are using for keeping tea hot for some time right now. So it will hold that hotness for around some 5 to 6 hours, right? So that we can consider it is almost acting as an isolated system. That's it. These are the 3 examples for this thing. Okay, next. So boundary can be also considered as 2 types. One is adiabatic wall and diathermic wall. So what is mean by diathermic wall means? So diathermic wall, it means there is a possibility for exchange of heat between system and surroundings. So heat can be exchanged between system and surroundings when this diathermic wall is used. And one more is adiabatic wall. So in this adiabatic wall means there is no exchange of heat between system and surroundings. Hope these terms are clear. Now let us enter slowly into the topic. Okay, right. So these terminologies are clear. So you can, this is for your reference to have that complete clarity. See, here I have a tea in this cup. So where it is closed, okay. So now this tea, our matter, and this the system, this matter containing system, in this system we have matter, okay. And this is the extra part is called boundary, what is that? Surroundings, that is separated by this imaginary or real boundary. So I hope everything is clear from the explanation and from these images. Okay, that's it. Next. So now the first question here, see, this is the first question from IIT JAM 2014. Very easy. Look at this. The 0th law of thermodynamics. See, what do we mean by 0th law first? See, first of all, why they named it as 0th law? First, before this itself, they have proposed first law and they have proposed second law. So there is no the other way to give the name. Therefore, they have considered it as 0th law. Okay. So what this 0th law, and why they mention it as 0th law? Because this law is very, very fundamental and very basic than this first and second law. That's why they mention it as 0th law. So what this 0th law says is, see, I have 2 containers. See, for example, I am making a the 3 containers. Consider there are 3 containers or whatever might be, you can consider here. So now this is A and this is B and this is C. You can consider there are 3 systems. Okay. Now this A and B are separated by adiabatic wall. So that's why I told you the basic term. What do we mean by adiabatic wall? There is no exchange of heat between system A and system B through this wall, because this is an adiabatic process, adiabatic wall now. So it will not transfer, it will not allow the transfer of heat from here to here. Okay. Now this A and C and B and C are in thermal equilibrium, means this red color wall here, it is what? Diathermic wall. This is what? Diathermic wall, which can allows the passage or transfer of heat from A system to C system and from B system to C system. Now what we know, if there is any temperature difference between this system C and A, there is a transfer of heat right now. It means these 2 are in thermal equilibrium. So I can say this TA, temperature of A, will be equals to temperature of C. Okay. And similarly this system B and C are also in thermal equilibrium like this. So I can say TB and TC are in thermal equilibrium, right? Right. So from these, what we can say, if these 2 are in thermal equilibrium and these 2 are in thermal equilibrium, then all 3 will be in thermal equilibrium now. See, from these what we can conclude, TA will be equals temperature of A will be equals to temperature of C, that will be also equals to temperature of B. It means all the temperatures of these 3 systems will be in equilibrium. See, it is how very basic, right? That's why it is mentioned as 0th law. Okay. So now what will be the correct answer for this question? Look at the options given. Gives a fundamental limitation of heat efficiency of heat engine? No. that is not the one. Next, it deals with the thermal equilibrium leading to the concept of temperature. Yes, it is discussing about equilibrium temperature. Na? So your option 2 will be perfect answer for this particular question. Hope this is clear. Yes guys, if this is clear, just mention clear in the chat box. Yes, yes. Let us move forward. Look at this. We have a question from the very basic terms again. So before going to solve this question, again this is 2014 question. Before going to solve this, you need to know further few more topics. Okay, few more very basic topics. Okay, let me explain all those things. Okay, so till now you have studied the basic thermodynamic terms. Now there are some thermodynamic processes. Thermodynamic processes. So what are these processes you can understand here is, first one I am saying isothermal process. Isothermal. What do we mean by isothermal process? Here isothermal, it means temperature is constant. If temperature is constant, change in temperature will be 0. What I am saying? Change in temperature will be 0. Okay, and similarly we have one more term called isobaric process. Baric, it means bars is a unit of pressure, na? So isobaric process means here pressure is constant. Iso means same, bar here pressure, so same pressure, so pressure will be constant throughout the process. So dP will be, change in pressure will be 0. Hope up to here it is clear. Next, third one will be isochoric. Isochoric means what? Here volume will be constant. Okay, so if volume is constant, dV will be 0. Okay, so these are very basic terms. Okay, you need to know this in order to understand the further topics of this thermodynamics. Next, one more I can say isothermal, isobaric, and one more we have adiabatic process. Adiabatic process. So adiabatic process means, for example, this is a system in which some chemical process or physical process is taking place. So there is no exchange between no exchange of heat between the system and the surroundings. Therefore we can say Q remains constant. In adiabatic process, what remains constant? Q remains constant. If Q remains constant, then dQ will be, change in Q will be 0. Okay, if something is constant, the derivation of that particular constant term will become 0. I hope it is clear. So constant, any constant you take, so derivation of that will becomes 0, because there is no change in that constant now for if you derive. So derivation is nothing but final minus initial. See, final and initial are same now, therefore the difference will be 0. That is what differentiation or derivation will be 0 here. That is what the dq, dv, dp, dt means. Okay, hope up to here it is clear. Right, let's move forward with few more terms here. Right, next one here you need to understand is thermodynamics properties. Thermodynamic properties. So you can expect a question from this, directly from this thermodynamic properties. Okay, so what do we mean by thermodynamic properties? There are some physical quantities, okay, whose values defines completely about that particular chemical process or thermodynamic process. So what I am saying, there are few properties whose values defines the complete thermodynamic process. Okay, so what are the types and what are they exactly? There are two types. One is extensive properties and other one is intensive properties. Extensive and intensive. So very easy to understand, look at here. So when to say extensive, so if the property depends upon quantity of substance, then you can say it as extensive property. So quantity dependent or mass dependent properties are called extensive property. For example, I am saying 5 apples will be having a weight of 500 grams I am saying. So now if I take 10 apples around, that might be around 1 kg, right? So now here mass depend upon quantity of apples, right? So I can say mass is a property which depends on quantity of matter. So those properties which depends upon quantity of matter can be considered as extensive properties. So what I am saying, quantity dependent properties are quantity dependent properties. These are called extensive properties. Okay, very easy guys, just look it here. Quantity dependency properties are called extensive properties. So you can take mass, otherwise in simple words you can define them as mass dependent properties are called extensive properties. Both ways are correct only. So now look at this, I am saying mass is a extensive property, and the next volume of a substance. See, volume of a substance. See, if I have a water of half amount, so I can say half liter, okay, and if it is full, we are considering it as a like 1000 ml, right? So now the quantity, like how much amount of water is defining whether it is half liter or 1 liter or like that, na? So I can say volume is an also example of extensive properties, because it is also depending upon amount of substance. So mass, volume, okay. So next length. See, if I have a substance having very small, it is of this much length only, so it is smaller, having this quantity is less now. So if this is bigger one, yes. So what I hope you got what I am explaining here. So length, and the next area, all this comes under extensive properties. Again, along with this, I am going to write some thermodynamic properties here, thermodynamic quantities. So internal energy, okay, which is indicated with symbol U or E, okay, and enthalpy, which is indicated with symbol H, and entropy, which is indicated with symbol S, and next Gibbs free energy indicated with symbol G, Helmholtz free energy indicated with A. All this comes under extensive properties, okay. Now comes to the intensive properties here. See, intensive properties means, very simple example I will tell you. See, what is a boiling point of water? If someone asks you, you will say at normal conditions you will be saying it as 100 degrees Celsius, okay. So 100 degrees Celsius is a particular point. Now you are saying that is a fixed quantity. It means whether you take half liter water or 200 ml water or just 10 ml of water, if you take, that is not a matter here. So both of them are, all of them are having the temperature of 100 degrees Celsius as a boiling point right now. So the boiling point of water is fixed here. So it means boiling point is independent of matter you are taking. It means independent of quantity you are taking, quantity of matter you are taking. So it depends only on, it is an it depends on individual property, individual substance right now. So boiling point of a particular, like water will be having some specific value, and some other quantity like you can take alcohol will be having some specific value, right, like that now. So what do we mean by intensive property? Quantity independent properties are called intensive properties. It is not like it doesn't depends on what quantity or how much quantity you are taking, okay. Hope this is also clear. So what are some examples you give me? Melting point, boiling point, these are some examples, and along with this density of water you are saying right now. So it means density is also an intensive property. So you can write mass or quantity independent properties, independent properties are called intensive. Simply you can remember intensive, independent. Intensive properties are independent, that's it, okay, right. So now how can you, what are the examples you can give here? Tell me for intensive properties. So just now I told you temperature, okay, and the next here with the temperature you will get melting point, and boiling point. Then next, what about freezing point? All this comes here. And what about surface tension? See, surface tension will be some specific value for a particular material, no? Yes, I mean I can write refractive index, all this this one which we will be studying in physics right now. So refractive index, surface tension, and then next what comes here. And one more thing, guys, density here we are writing now. Density is also intensive property we are writing now. So if you observe density formula, how it will be? Density will be mass by volume. See, mass is an extensive property and volume is also an extensive property. So the ratio of two extensive property is an intensive property. So here I am writing the ratio of two extensive properties will be an intensive. Okay. And next, see, area is an intensive property here, extensive property here. Force is also an extensive property. So now pressure will be intensive. Why pressure will be intensive? Pressure will be force per unit area, F by A. So if it is both of them are extensive, the ratio will be intensive. Pressure will be an intensive property, you can remember. Hope the concept is clear what I am explaining. What do we mean by extensive and intensive properties? Based on this, you can answer me any questions in the exam also. Okay, right. So the next, after this, what are the other things you need to know here is, see, if this is a system, what I am saying, if this is a system, I am passing Q amount of heat. What we are giving? Q amount of heat is given, supplied to the system. So that is nothing but heat absorbed by the system is Q. So when I am saying heat is indicated with symbol Q. If heat is absorbed by the system, then you should say Q is positive. So with the perspective of system, you should answer. So heat is absorbed by the system means Q should be positive here. Now if system is releasing some heat, if Q is released, so minus it is, okay, it is plus. So heat released by the system, it means heat is coming out of the system now. So that is what releasing, you can indicate with symbol negative, that is Q will be negative, that is Q is less than 0 here. And here Q is observing now, Q is greater than 0 here. You can understand in this way. Now one more thing is there, if this is a system, we are doing some work on the system. So work done on the system. So this is work done on the system now. See if it is absorbed by the system or on the system. So you should give positive symbol for that. So W will be positive here and you can indicate with W greater than 0 here. Okay, based on this only we have a next question from IIT JAM. Okay, and if heat is coming out of the system or work is done by the system, this is work is done on the system. Sometimes work is done by the system. It means work done by the system. I will explain this. Work done by the system. So here work should be indicated with negative. So this is less than 0, that is greater than 0. Hope this is clear. Yes, based on this understanding, you just answer me this one. Look at the question. Water is injected into a balloon filled with ammonia gas. So this is a balloon, you can understand, you can consider this as a balloon. So in which ammonia gas is there. Okay, so into this water is injected. So water is injected here. Okay, so the next what happening here? So balloon shrinks. So what happens? Balloon is shrinking. So it means shrinking means initially it is having V amount of value. So it is now becoming V minus some amount is decreasing right now. So volume is decreasing here. So change in volume will be negative right now. So change in volume will be negative. You keep it aside, I will explain that. And the next. And it is hot to touch. So when this process is happening, when I touch this balloon, feeling hot, it means what? Heat is coming out of that balloon, therefore we are feeling hot. So I can say heat is released by the system now. If this is a system, heat is released, that's why we are feeling hot to touch. So I can say Q is negative here. So Q is less than 0. So where do we have this option? Q less than 0 in option 3, option 4. So you can remove 1 and 2. So out of 3, 4, there will be one option. I will tell you how can we predict that one also. Okay, look at this. See, work. How can we define this work? See, work is nothing but force into displacement. Okay, dx we are writing. So force I can write. See, pressure is nothing but force per unit area. Na? So force, in the place of force I can write pressure into area. Right now, so here I can write PA dx. Dx means displacement, you can consider. So area L square and length, this is displacement, length only now. So I can write this as D into area into L. So it becomes, area means L into L now. So L into B into H, it becomes L cube. That is nothing but volume. So change in some length will be there. So it means volume changes here. So W you can write, mechanical work will be equals to, W equals to P dV. And when it comes to chemistry thermodynamics, so we will be using a symbol like W equals to minus P dV. So what is this, what is the use of this minus here? So that minus symbol says work done by the system. It means, for example, see just try to understand what I am explaining here. Here I have a piston fitted to this container. So this piston can move up and down easily. Okay, you ignore its gravitational force and all. Okay, it can able to move up and down freely. So now what happens inside this container? I have some gas. Let us say some ideal gas is there. So now when this gas is expanding, initially the volume is V1. If I am saying gas is expanding, it becomes V2 now, right? So now what happened if this is expanding, therefore the piston moves up to here. So if it is moving up to here, the volume is expanding now. So if volume is expanding, so you can say work is done by the system. What I am saying, work is done by the system. If volume is expanding, so change in volume will be dV will be equals to V2 minus V1. That is V2 is greater now, so dV becomes what? Positive here, right now. So it becomes positive. So now if I place this pressure as a constant one, the external pressure is constant here, P external is constant. So volume here it is positive. Okay, so now what it is indicating, W will be, so this is complete term becomes negative. So when I told you about this previously in the previous slide, the work done by the system should be indicated with a negative symbol. That's why we got here negative. That's it. Okay, hope everything is clear. And if it is work done on the system, so dV becomes negative, negative into negative, positive. So that is work done by the system. Here work done on the system. This is work done by the system. If it is negative, by the system. Okay, by the system. If positive, work done on the system, you can remember. Okay, by understanding these two things, you can answer me this one. See, what is the final formula we have? P dV, W equals to minus P dV. See, balloon is shrinking. So shrinking means what happens to this term? See, the final volume becomes less now, shrinks means it compressed. If it is compressed, final volume is decreased. So V2 minus V1 becomes negative. So negative into negative becomes positive. So if it is positive, work done on the system, that is positive. Where do we have positive here? Yes, this is a positive, this is negative. So ignore this. So option 3 will be a perfect answer for the question. Hope this is also clear. Right, let us move forward. So here we have a question. This is based on first law of thermodynamics. See guys, I am trying to continue this session with very proper sequence by looking at the questions, so that you will get what you are learning and why you are learning exactly. Because we need to go for this PCM subjects, definitely you should follow what type of questions asked in the previous exams. In the same pattern you can make your preparation, because that will saves your time and make it more productive and more efficient preparation right now. So that's why I am showing the question first, then I am teaching you what you are going to learn. Okay, right. See here, there is something called first law of thermodynamics. So what this first law of thermodynamics says, so this is nothing but you have studied it from very basic, I think so. See, the total energy of the system or whatever you are taking will be conserved. Okay, so what I am saying, energy will be conserved, or we can say energy can convert from one form to another form. Okay, like mechanical energy becomes some other thermal energy or something like that. So energy can transform from one form to another form, okay, but it cannot be destroyed or it cannot be created, but it can be transformed from one form to another form. This is what the basic definitions we have. Okay, so when it comes to the mathematical representation of first law, so you can take here this is a system. Okay, so every system will be having some energy internally, okay, called as internal energy U1. Okay, so to this system we are supplying some Q amount of heat, therefore its energy becomes now Q1 plus U1 plus Q. Again we are doing some work on it so that it becomes now U2. So now what is this U2? U2 is equals to Q1 U1 Q1 plus U2, this W right now, W U2, and this one will be our U2. Okay, so now U2 minus U1, that is final internal energy minus initial internal energy is nothing but Q plus W. That's it now. This is what we got, Q plus W. So what is our first law of thermodynamics? Delta U equals to Q plus W. That's it. This is what you need to remember. Okay, so based on this we have lot of questions in the paper. Okay, so and it will be useful for in other cases also. I will show you. Okay, so what you can remember, the total energy of universe remains constant. If someone asks you what is the first law of thermodynamics, mathematically you can give it like this, or theoretically if you want to say the total energy of universe remains constant. Okay, what I am saying, total energy of universe remains constant. This is what the first law of thermodynamics. If someone asks you the second law of thermodynamics, you just say the entropy, it will tell us about the entropy. The entropy of universe keep on increasing. Okay, what I am saying, the entropy of universe increases spontaneously. Okay, so first law says energy remains constant, and second law says entropy increases to the universe. Okay, for an isolated system, the entropy of that system always increases. Universe is the best example of isolated system. Okay, so the entropy of universe increases and increases to maximum or tends to maximum, and energy remains constant. These are the combinations of first and second laws of thermodynamics. Okay, right. Look at the question now. 1 mole of gas absorbs 40 joules of heat. So Q absorbed is how much? 40. Absorbed now you can mention it as positive. Okay, if the work done on the surroundings by the system, work done by the system, it means W is negative. That is how much? 20 joules. That's it. Over. That's it. You need to take in these values data in the proper way, so in order to get the exact answer. So delta U is equals to Q plus W right now. So Q is what here? Heat. So heat absorbed by the system now, so that is plus 40. Okay, and work is done by the gas. It means work done by the system means it is minus 20. Okay, so this will be 40 minus 20, this will be 20. That's it. This will be the perfect way of taking the values, so that you got an answer as option 2. Okay, see the remaining related options are also there just to make you confused. I hope you got complete clarity on what we are discussing and what type of questions are asked. Let me give you one question. Those who are in the live session can answer me in the chat box for this particular question. What will be your answer for this? Yes, anyone, those who are watching this, whether it is whether you are a live student or a recorded person, I mean if you are watching after recorded also, you can answer me in the chat box for this particular question. What could be your answer? A system does 100 joules of work on surroundings by absorbing 150 joules of heat. calculate the change in internal energy. Yes, you can try. Okay, yes, let me give you this. Yes, you can try this and you can answer me this. What will be your answer for the question? Yes, you can try this. If you are, it's very simple, like as we have discussed previously. In the same way you can answer me that. Okay, so even if it is wrong, no issues, but just give a try, because very simple question. Give a try. If you are unable to answer, I will explain in the chat box, but you must answer me your answer in the, your response in the chat box. Okay, I will be looking into it and definitely make it correct. Okay, right. Next, look at this. During a cyclic process, which of the following is not always 0? Okay, so you need to understand one more thing here. Okay, so there is something called cyclic process. It's a simple cyclic process means the thermodynamic process. What are the processes we have studied? Isothermal process, adiabatic process, isochoric process, isobaric process, like this we have studied now. If those process is operated in a cyclic manner like this, or in this cyclic manner, okay, starting from one point and again ending at the same point, we can consider them as cyclic process. That's it now, I hope you know. So now in this cyclic process, the change will be 0. Okay, what I am saying, for a system operating in cyclic process, its energy change, like internal energy change, will be 0. So why I am saying this as 0? How can you know whether it is 0 or not? So again you need to know the two terms here, state function and path function. What you need to know? State function and path function. So state function means these thermodynamic properties whose value, the total net change, depends only on initial and final states of the system. Initial and depends only on initial and final state of the system, and it is independent of how path is followed to attain that final state. So it is independent of path followed, but it depends only on initial value and final value, that is initial state and final state. Okay, when it comes to path function, so you can understand this path function. I will give you complete examples of state function and path function, no worries, just look at here. See, when it comes to path function, it depends on how final state is obtained, or reached from initial state. It means it depends on path. It depends on what? Path followed by the system. That's what we are saying it as path function. So best example here are heat and work done. These are the two examples. See, work done, for better understanding, look at this. Work done, whether it is state function or path function, you can understand in this way. See, you are at this point and you need to reach this point right now. So in order to reach that point, from this initial point to this final point, you can have a n number of paths, right? So you can go in this way like this to reach this final, or you can directly move like this. This is the shortest distance. Now if you go in this shortest distance, you will be consuming, or you will be wasting your less amount of energy right now. Okay, so you will be having less work here. But if you go in this way, the work you are doing in this way will be more now. So it means what? The quantity of work you are doing depends on how the path you are following, whether this path or this path. So this kind of things, the path dependent properties, okay, are the things which are depends on path followed, will be considered path functions. Best example here, heat and work done. Okay, when it comes to state functions, It depends on initial and final state of the system and independent of this path followed. The best example here are pressure, temperature, volume change, okay, see these things, and entropy, enthalpy, Gibbs free energy, internal energy, Helmholtz free energy, all these things are state functions. You need to remember these things, okay. So best way to remember here is pressure, temperature, volume, okay, PVT, PVT, next this entropy, enthalpy, Gibbs free energy, internal energy. See what I am saying, free, whenever I use the word free energy, those are extensive properties as well as state functions. See Gibbs free energy I am saying, Helmholtz free energy I am saying, these are both state functions and extensive properties. Internal energy and enthalpy, these are also state functions. One more is entropy. So these are state functions, and all these are what? All these are extensive properties also, you can remember, okay. And one more thing, for a state function, this is very, very important. Based on this statement only, we have one question in IIT JAM. Look at this, what they are saying. For a state function, operating in cyclic process, the change is zero, the net change will be 0. I will tell you what exactly it means. See, this is the indication of a cyclic process happening in cyclic process. If z is a state function, its value change will be equals to 0, dz will be 0, okay. Hope this is clear. I mean, if I say there is a pressure operating in this cyclic process, the change will be equals to 0, you can consider, okay, right. Next, for your understanding, you can get more clarity if you want, if you are still having confusion. If I am doing a work in this pressure volume here and pressure here, okay, if I am saying this is something like 10 atm pressure, this is 5 atm pressure, okay, and this is 5 liters of volume, this is 10 liters of volume, you can consider. Now just you can operate this cyclic process in this way. See, this is 1, 2, 3, 4. So now what are the process involved? See, during this process from here to here, volume is constant. So first process is isochoric process. From here to here, pressure is constant. The second process is isobaric process. From 3 to, so this is second, this is third one. So in third process, again isobaric process, isochoric process, volume constant, see. So this is isochoric. And what about this? Again pressure constant, so isobaric process, 4, okay. So if you want to change, if you want to find total net change pressure, total change in pressure in this process, this is a cyclic process now, so total change in pressure will be how much if you want to calculate. Just check here at point 1, at point this A, B, C, D, if you consider, just look what happening here. Point A, B, C, D, if you want to take, yes, you can look at point A, what is constant here? Volume is constant right now. So volume is constant and pressure is P1 plus P2 plus P3 plus P4 if you take, change in P1, P2, P3, P4 if you take. So what happens here? From A to B, from at point A, what is the pressure you are seeing? See, from this process 1, I can say final is 10 and initial is 5, that's it. At second process, final is 10, initial is also 10. So this will be 10 minus 10, 0. And P3 if you observe, so final is 5, but initial pressure here is how much? Initial pressure is 10. So like this. And P4, P remains constant 5 only, so P4 will be 0. So what is the final change in this process you got? Here plus 5, there minus 5. So the net change will be how much we got? 0. So like this. Now it is depending on initial and final paths only now. So if initial and final paths are same, I mean initial step and final state is same, then we can say the change will be 0. That's why in this cyclic process which is operating, it's a state function operating in cyclic process, change will be 0. Hope this is clear. So same story applicable for all these thermodynamic properties examples. Okay, and when it comes to thermodynamic property state function examples, when it comes to path function, it might be 0, it may not be 0. Okay, it depends on individual cases, but for state function, if it is happening in cyclic process, always it is 0. Now look at the question. During a cyclic process, which are the following is not always 0? If it is a path function, it will not be 0 always, right now. If it is a state function, always 0. See, enthalpy, state function, entropy, state function, internal energy, state function. For them, cyclic process happening in state function happening in cyclic process 0. So work done, if you observe, this is not a state function, it is a path function which may not be 0 all the case, right now. So fourth option will be perfect answer for the question, right? Next. Again look at this question. What the question says, see, again I have given this question as a homework, right? So you can try and you can answer me in the chat box if you know that answer. Okay, and then next we'll come back to this. So next, if you look at these, you will be having something like relation between delta H and delta U. So what I told you, U means internal energy. What is that? U means internal energy and H means enthalpy. Okay, so again internal energy, see, any system you take any substance, there will be some energy associated with it internally, that is nothing but the internal energy E or U you can use to indicate will be equals to sum of its kinetic energy plus potential energy, I can say, or that particular substance, particular matter, whatever you take. So it will be having some molecules or atoms now, so that atoms will be associated with some vibrations, okay, and some translations or some rotations. So that will generate energy. So if it is undergoing translational, so we can have translational energy, E translational. What I am saying? E translational. Okay. Similarly, if it is undergoing any vibrational, so E vibrational you can write, and you can write E rotational like this, and E energy of bonds, bond energy, like this. So many energies are there. The sum of all these types of energies is called as its internal energy. That's it. Okay. Now, how this internal energy can be given in a formula pattern, okay, or how it will be changed? I told you internal energy is a state function and it is an extensive property. It is what? Extensive property. This is also extensive property, you can say. And then next, it is also state function. Both of them are state functions only. Okay. And the next, see, for a state function operating in cyclic process, what happens? The change will be 0. Internal energy change will be 0. Enthalpy also 0 if it is operating in the cyclic process. Next. So, internal energy indicated, see, exact E value we cannot calculate. Exact internal energy value cannot be calculated. So, we will be only doing change in internal energy calculation but not exact values, okay, because it is associated with very small energies, so that values keep on changing. Therefore, exact value of internal energy cannot be calculated, but change in internal energy can be calculated. Okay, it means during a process from 1 to 2 state, what is the energy change associated during this transformation can be calculated as delta U. That's it. Okay. But exact value cannot be calculated in case of internal energy as well as enthalpy. Okay, right? Because it depends on microscopic level. But our thermodynamics do not discuss about microscopic. It depends only on macroscopic bulk properties only. Okay, that's it. Okay. Next thing is, here I hope up to here it is clear, right? So now they are asking what is the relation between both of these things right now. See, I am writing. du is equals to dq plus dw. So where we have seen these? We have seen this in the first law of thermodynamics. This is the first law of thermodynamics. So du is nothing but u2 minus u1 I am writing, and dq like change in heat. Okay, so change in heat I am writing dq as it is. So for this, for understanding purpose, what I am making, just see, dq I am writing, which is equals to du minus dw, okay, and du means u2 minus u1 minus du means pdv, okay. So at constant pressure, it means the heat content of the system. For example, if this is a system having some heat energy associated with this, if I am measuring this value at constant volume, I can say it as its internal energy. But if I am measuring the heat content of the system at constant pressure, I should call it as enthalpy. Why I should call it as enthalpy? Just look at this thing what we are going to get. U means internal energy at some condition U2, I am saying U2, and this PdV means I can write PV2 minus PV1 right now, U2 minus U1. So what we will be getting from here, U2 this minus of, see, PdV we have like this. So from this dW means what? Minus PdV, no? So minus of minus, that becomes plus here, okay. So U2 plus PV2 minus U1 plus PV1, that's it, okay. So this is nothing but to the internal energy some more quantity is added, so that together this new quantity is considered as enthalpy H. So at value 2, so H2 at temperature some higher temperature, let us say some T2 temperature, so H is called H2 and this is H1. So this difference is called H1, this difference is called dH, okay. This is what enthalpy change, that is nothing but heat content of the system measured at constant pressure, okay. If it is measured at constant volume, that is dQV is equals to du. Why we are saying this relation, how, from where we got this relation? Again from first law of thermodynamics, from this first law of thermodynamics, see dQV I am saying du plus dW, okay. So if dW, look at this dW, this is nothing but P minus PdV now. If volume is constant, if V is constant, what happens? This change in V will be 0. This second term becomes 0. Therefore dQV will be equals to du. So it means internal energy change will be equals to heat content of the system measured at constant volume. Hope the discussion we have did till here is clear, right? Next, let me show you that question. So finally, what is the relation we got between enthalpy and internal energy? dH equals to du plus PdV, okay. From ideal gas equation we have PV equals to nRT right now. So from this I am applying delta on both sides. If since it is an ideal gas, that's why I am rating it as Ng gas, okay, right. So here in the place of PdV I can write delta NgRT now, that's it. This is a very important equation, du plus delta NgRT, okay, right. So now this equation we need to use for solving this kind of questions. See, which are the following reaction delta H is equals to delta U? So delta H should be equals to delta U, they are saying, but we have relation something like this. It means if delta Ng value is 0, the second term becomes 0, therefore it will be equal. So when that will be equal, just check, see, number of gaseous products and reactants must be equal. See, gaseous products are how many here? 2. Gaseous reactants are how many here? 1 plus 1, 2. So this will be 0, yes, it is perfect. See here this graphite, carbon is in graphite form, it will be solid form, okay, it cannot be gas. Consider only gases. So this is gas now, so how many are there? 1, and here this is also gas now, this is 1 by 2. So you will get 1 by 2, this is not equals to 0, okay. So first option is 0, it means the second term becoming 0, delta H will be equals to delta U in option number 1, okay. Similarly you can cross check for other options also. And where you can get these PYQ questions? Yes, these PYQ questions are available with Chandu Biology classes for all IIT JAM, whether it is bio questions or your core subject question or this PCM subjects. Everything will be available with this CBC. You can contact to the mobile number given in the description box, okay, and also on the front page of this of this channel, okay. So I hope everything is clear, and for your practice purpose I just want to show you this particular question. I know you can easily answer this question based on our previous discussion, whatever we have discussed, and if you know the concept of thermodynamics, you can try this based on Hess law. Yes, the remaining things we are going to discuss in the next session. I hope you enjoyed this session and it is highly helpful for your preparation, right guys. So thank you for watching. Stay connected with this Chandu Biology classes. Thank you for watching.